Alright, 3.3, polynomial and synthetic division, and long division. So we're going to look at long division to divide polys. We're going to use synthetic division to divide polys in the form of x minus k, which is going to be very important for factoring later on, and we're going to use the remainder and factor theorems. So one of the things that I have to stress right off the bat is that long division is not changing. It is still the same general algorithm. We're just going to use the language of math to explain it. So here we go. And if I'm going to take 1,574 and divide it by 3, well, we just have to ask ourselves how many times does 3, and this is a nice number. It's just a single-digit number, but we're going to break all of the other ones into single digits, you'll see. So we just have to ask ourselves, how many times does 3 go evenly into 15? Because it doesn't go into 1, so we have to go into 15, and that's 5 times. So then we ask ourselves, well, what is 5 times 3, which is 15? Then we apply the subtraction, right? Just for our algorithm. And then we do the subtraction and we bring down the next number, right? And obviously this is 0, so we'll just sort of cross that out for right this second. And then we ask ourselves, how many times does 3 go into 7? Well, that's twice, so we'll put a 2 there, and then we'll do 2 times 3, and that's 6, and we'll place it there, and then we'll make sure that we subtract it, and then we'll do the subtraction. We have a 1 this time, and now we bring down the 4. So now we ask ourselves, how many times does 3 go into 14? And we can go into it 4 times, so that 4, it's getting a little cluttered here, 4 times 3 is 12. Then we do the subtraction, and we have a remainder of 2. So what we have here is that, well, let's write it first. So we have with a remainder equal to 2. I think that's how most people see it first. But what we can do is also rewrite it this way, right? 524 plus 2 over 3. Or we could simplify this to, well, let's not do that right now. You can simplify it down to the improper fraction. But what this is very important because one of the things that we can see is that we're generating factors. And if we look at this, we can see that 1574 is actually equal to 3 times this beastie here. So we have times 524. And then what we have to do is add 2 to it. And if we do all this out, we are in fact going to come up with the same value, 1,574. And if we look down here now at the division algorithm, it states that if f of x and d of x are polys such that d of x does not equal 0, so that's the denominator, and the degree of the denominator with respect to x is less than or equal to the degree of the function relatable to x, then there exist unique polynomials q and r of x such that f of x, and this is where it gets really nice, is f of x is equal to the denominator of x times the quotient of x with the remainder of x being added on. And I'm hoping you can see that here's the divisor there, and we have the quotient, which I can do in orange here, and then the remainder, light green, if you can see it, light green, and I'll just do that over here, down here too. So literally, we're just stating in an algebraic sense what we just did with the division algorithm that we learned so long ago. So when the remainder is 0, or the degree or r of x is less than the degree of d of x, if the remainder r of x is 0, d of x divides evenly into f of x. And we can also express it here, as I stated, and if I go all the way back up and I put a box around the 524 plus 2/3, you can see that that's the same thing. So make sure the exponents are counting down, left to right, and make sure that to account for all possible degrees, okay? And that will be very easy to see. What we'll call them is placeholders. Okay. Synthetic division is a really beautiful way to do long division in a controlled and very fast manner. So if we want to divide any polynomial, this happens to be a third degree polynomial, by some factor x minus k, then we simply take the opposite of what we're looking at, so we actually calculate the 0. So technically k is the 0, all right? And we perform this operation here, and if, it's a little difficult to see, but I think if you see it in the example coming up, that it'll be very clear. But we just multiply the 0 times the lead coefficient, and then we pop that product up, combine the KA, so this combination right here would be KA plus B. And then we repeat the same process over and over again. All right. So the remainder theorem is great because it states that if the function relatable to x is divided by the factor x minus k, then the remainder is r equals f of k. And what that really is, we'll look at that in a specific example, but it's really nice because then we can generate, if not only can we generate the zeros, but we'll also be able to generate one single solitary point. So if at the 0 we can evaluate it, we'll get a remainder, which is this value right here, and that will tell us that that's the output value, so it'll be the output at f of k. Okay? So that's a very important one because it'll give us another point. The factor theorem states that if f of x has a factor x minus k, if and only if the function evaluated at k equals 0. So again, it's just stating that that's where it's crossing the x-axis, where the y is equal to 0, and that is a 0. Again, so it's just saying that if we find a 0, we can turn it into a factor, and then we can actually use that to graph and subsequently get an idea of what the graph looks like. All right, let's start looking at some specific examples. And here we're going to use long division to divide the following. And you'll notice right off the bat that the first polynomial that we're looking at is not in standard form. The degrees are not decreasing. However, we do have all of them. We do have the highest degree is a 3, then we have a 2, we have a 1, and the constant. But just to remind everybody, we can rewrite this also as 3x plus 2x cubed minus 9 minus 8x squared, all divided by x squared plus 1. So these are equivalent statements, and just wanted to remind everybody about it. But what we first need to do is put this guy into the correct form. So let's do that. The biggest degree is 2x cubed, and it's positive, so I'll write 2x cubed. The next one is an x squared, but it's negative, so I'll write negative 8x squared. And then I'll see that there's an x to the first power, and that's positive, so that's 3x, and then minus 9. So now we have the poly in the nice form. Okay. Now we can do the long division. And we don't need any placeholders because we do have all of the degrees. So notice right here, all degrees present. Whoops. Okay. So no placeholders needed. Alright, so let's actually carry out the algorithm. And here's where it gets a little bit interesting, and I'm going to try to do it. I'm not sure if this tablet will allow me to erase and show you the same thing twice, but I don't really think it does. So we'll do our best here. Alright, to carry out the long division, what I want you to do is sort of forget that this highlighted version exists, and only focus in on the x squared, the first term that you see. Okay? So here what we have to do is ask the same question. How many times does x squared go into 2x cubed? So how many times is that? Well, how many times do I have to multiply x squared to get an x cubed? Well, that's an x, so we'll need 1x here. And how do I get 2? Well, that'd be by 2, multiplying by 2, so it looks like what we have here is 2x. And now we're going to multiply this 2x all by the entire expression x squared plus 1 now. So now we have 2x cubed plus, well, it looks like what we'll have is 2x. So notice where I put them. Okay, so hopefully you can see where I place them under the common terms, right? Alright, and now what we have to do is remember to subtract. Now at this stage, when you do the subtraction, what you're really doing is just changing all of the signs. So this would now be a negative, and that would now be a negative, and now we just do the same algorithm. That is going to cross out, give us 0. We'll bring this down, the negative 8x squared, and because it didn't have anything, so we'll just keep that where it is, and then we'll combine the other ones as a plus x. And then we'll bring down the negative 9. Okay? So the only reason why we weren't able to cancel out the 8x squared, but that's okay. So let's go on to the next one. Again, try not to focus in on the plus 1, but focus in on the x squared. And now we want to ask ourselves, well, how many times does x squared go into 8x squared? So remember, we're going to have to change the signs, so it looks like we just have to match the signs, and in order to match, because we want to match negative 8x squared, right? So we're going to have to multiply negative x squared by 8, and it must be the negative, right? So that would give us negative 8x squared. That would cancel out that highest degree, and then minus 8. And then, remember what we have to do at this point. I'll use blue again here. That at this point, we're going to be doing a subtraction. So again, we need to change the signs. So I'll put them in like this. And now those will cancel out, leaving x minus 1. So what it looks like now that we have is the solution, or what this breaks down into is 2x minus 8 plus x minus 1 all over x squared plus 1. Now, also we could write this as that's the whole mechanism. If we actually write it in as 2x cubed minus 8x squared plus 3x minus 9, and all of that would be equal to the 2x minus 8 times the x squared plus 1 plus x minus 1. So all of those are ways of representing that long division. All right, now let's move on to example 2 using synthetic division. And the very first thing that we'd like to do with synthetic division is find the zero. And we're going to talk more about this, and I keep talking about it now, but we do go into much more detail. But literally, it's just crossing the x-axis. So even though we will go into more detail, it's pretty much just that. So we want to find the zero to use for the synthetic division. So that just means that we're going to take whatever we're dividing by, in this case the x plus 2, and let it be equal to 0. In this case, we now know that a 0 exists at x equals negative 2. So what we're going to do now is take negative 2 and use that as our little guide to start out with here. Okay, so now all we have to do are take the coefficients. So I'll try to do this in a different color. And notice that we don't have all of the degrees. So in the first, maybe what I'll do is do it this way first. So what we're going to need are the x cubes, because that's the biggest degree. Then we're going to need the x squares. Then we're going to need the x to the first, or just the x degrees. And then we'll need x to the 0, or the constant degrees. So if I do this now and I look at 5, well, 5 would go here. And then, well, we have nothing for that, so I'll put a 0 in that placeholder for the x squared, because we don't have any of them. And then we'll use the plus 6 for the coefficient here on the linear term, and on the constant, we'll use that plus 8. Okay? So here's how the process works, and I'll do it, well, yeah, I should probably just use black. So in the first case, we always bring it down. Okay? Then what we do is we multiply, what color can I use? I guess I'll use red. We multiply the negative 2 times the 5, and then we place that value, that product, up in here. So that would be negative 10. And then we combine what's in that column. So 0 and a negative 10 gives us a negative 10. And now we multiply, so we follow the same process now, the negative 2 times the negative 10, which gives us a positive 20. And then we combine the 20 and the 6 to make 26. And then we actually carry out the last process here, and maybe on pink, negative 2 times 26, well, that's just a negative 52. So if we combine all of these together, that'll give us a negative 44. And I'm going to make a little box around that because it's the last piece, which indicates to us that that's the remainder. Okay? So then what we do is we look at the shift, and we're losing one x as we go down. So at this stage, after everything is done, this becomes the x squared. So we're losing 1 degree across the board. That would be x. That would be the constant, or x to the 0, and then this is the remainder. So if we wrote this all down, we would now have 5x squared minus 10x plus 26 plus the remainder of a negative 44, all divided by x plus 2. Now, we can also rewrite that as this. We could say 5x squared minus 10x plus 26 minus 44. is also a suitable answer. So there we go. There's the pattern for synthetic division. All right, so let's look at another example, and we're going to have to write the function in the form f of x equals the quantity x minus k times q of x plus r, or the remainder theorem. So, and then we're going to have to prove that the remainder theorem actually works by giving us that point f of k equals r. So the easiest way to do this is, since they already gave us k, is to use the synthetic division. So let's set that up, and luckily for us we have all of our degrees, so just make this a little bit higher here. The first one's 1, then it's negative 5, then it's negative 11, then it's a positive 8, and now we can begin the process, right? So we have 1, that looks like negative 2, then when we combine them we get a negative 7, so that looks like 14, and when we combine those we have a negative 11 and a positive 14, so we have 3, and then we have a negative 6, because negative 2 times 3 is negative 6, and then we combine the 8 and the negative 6, we get 2. That's the last piece, so we have a remainder, and what this is suggesting, remember, is that f of negative 2 is equal to 2. So if this is the case, then we've also demonstrated it, okay? So now we can actually write the first form, so as f of x is actually going to be equal to, in this case, because k is a negative, it's got to be the factor x plus k. You know what, let's just put what it actually is, 2, right, because that's the opposite of negative 2. And then we have to multiply it by the pieces that we did from the synthetic algorithm here. So that in the original one it was x cubed, so it would be x squared, because we lose 1 degree, minus 7x plus 3 with a remainder of 2. So we've now just satisfied that first requirement, and now let's prove that it does in fact give us 2 when we do that. And the way to do it is I'm just going to use this function here that we just generated and use that. So f of negative 2, and that's equal to negative 2 plus 2. Well, there's our 0, and negative 2 quantity squared minus 7 times negative 2 plus 3, and all of that plus 2, and we're good to go. That looks like all that's going to be 0 plus 2, or f of negative 2 is in fact 2. So we did demonstrate. Now you can do that also with the original function up here, which is probably better, but I'll let you do that one on your own. Alright, now let's look at our last example, and we're going to use synthetic division to show that x is a solution of the third degree polynomial equation, and use the result to factor the polynomial completely. We're going to list all the real solutions. Okay, so let's get to this, and we can see that we're saying at this point that x is a solution, but we have to show that. In order to show that, what we have to really do is make sure that there is no remainder. Okay? So let's do the synthetic division. So we're just going to take, in this case, what was I saying? Oh yeah, we're going to take the negative 4 here, because we want to see if that is in fact a solution to this problem. And let's do it out. So what we have here is, let me just make sure, x cubed, x squared, x, and x to the 0. And that looks like what we have is 1, 0, negative 28, and a negative 48. bring the 1 down. That's a negative 4. That's a negative 4. That's 16. That looks like a negative 12. Negative 4 times negative 12. It looks like it's a positive 48. And that is, in fact, a 0. So at this point, we now know that x equals negative 4 is a solution to the poly. Now it asks us to completely factor it. So what we now know is that x cubed minus 28x minus 48 is equal to the factor x plus 4, right? Remember, this is opposite of the x. So because x is equal to negative 4, this has to be the opposite to get back to 0. So remember, we're trying to get back to 0. Okay? And then we have the next polynomial, which I'll highlight here, without the remainder, is, maybe I'll do it in red. And remember, all of the degrees go down by 1, so what we have here is going to be x squared minus 4x minus 12. And now it says to completely factor this. So now we have to ask ourselves, is this factorable? So are there factors of 12 that will combine to 4? Yes, there are. There is 6 and 2, right? Because 6 times 2 will give us 12, right? And one of them has to be negative. And B in this fact is negative 4. So it looks like negative 6 plus 2 would give us the negative 4. So this is factorable. And what all this would equal now is x plus 4 times the quantity x minus 6 times the quantity x plus 2. And all of that is the factored form of x cubed minus 28x minus 48. Now, so this would be the expanded form, and this would be the factored form. Okay? Now, from the factored form, we can actually find the solutions. So the solutions exist at the places where each one of those would be zeros. So x plus 4 equals 0, x minus 6 equals 0, and x plus 2 equals 0. So when you solve those, you can see that at x equals negative 4, which we already knew, x equals 6, and at x equals negative 2 are the solutions. So solutions exist at these values.